All right, today we're cracking open one of the greatest detective stories in all of science. We're going on a hunt for the answer to a huge question. What is our universe really made of at the tiniest, most fundamental level?
So, just take a second and look around you. I mean, everything. The screen you're looking at, the chair you're sitting in, even you. What's it all made of? What's the fundamental stuff? For thousands of years, that was a question for philosophers. But today, thanks to some incredible detective work, we actually have an answer.
And that answer is atoms. Everything, and I mean everything, is made up of these ridiculously tiny particles. But just saying it's all made of atoms is kind of like saying a car is made of car parts. It's true, but it doesn't tell you anything. The real mystery, the fun part, starts when we ask, what's inside the atom itself? Okay, so to figure this out, we've got to meet the cast of characters, the suspects, if you will, that are hiding inside the atom. And it turns out there are three main players we need to know about. And here they are. First up, you've got your protons. Think P for positive charge. Then you have the neutrons, and just like the name sounds, they're neutral, no charge at all. And finally, the electrons, which have a negative charge. Now check out that relative mass column. Protons and neutrons are the big guys, the heavyweights in the atom. The electron, it's tiny, like almost 2,000 times lighter. It's basically a feather compared to a bowling ball. And trust me, that little detail is going to be a huge clue later on. So, how do we keep all this straight? Well, chemists have a pretty simple system. We use two key numbers. First is the atomic number. We call it Z. Think of this as the atom's social security number. It's just the count of protons, and it's what defines the element. So for calcium, you see it's 20. That means every calcium atom has 20 protons, period. Then there's the mass number, or A. That's just the total count of the heavy particles, so protons plus neutrons. See? Pretty straightforward. Okay, so we know the players now. Let's jump in a time machine and go back to 1911. At this point, scientists knew atoms had positive and negative bits, but they had no clue how they were arranged. Was it like a chocolate chip cookie with bits scattered around? Nobody knew. So a physicist named Ernest Rutherford decided to do something brilliant. He was going to take a shot in the dark, literally, to see what was inside. And the setup for this experiment was just beautiful, so simple. Basically, Rutherford and his team took a source that shoots out these tiny, positively charged bullets. They're called alpha particles. Then they aimed this stream of particles at a piece of gold foil that was incredibly thin, practically see-through. And then they wrapped a detector screen around it all to see where the bullets ended up. Simple, right? So they turn on the machine, and the first results start coming in. And at first, nothing surprising happened. Almost all of the little alpha particles just zipped right through the gold foil like it wasn't even there. Okay, clue number one. This seems to mean that atoms are mostly just empty space. Makes sense. No big deal. But then they looked a little closer, and they saw something weird. A few of the particles didn't go straight through. They were getting bent, pushed aside just a little. Now remember, those alpha particles are positive, so for them to get pushed away, they must be getting close to something else that's also positive, like trying to push two magnets together the wrong way. Interesting. And then came the observation that completely blew their minds. This is the moment the whole story changes. A tiny fraction of the particles, we're talking like 1 in 20,000, didn't just get deflected. They hit the foil and bounced almost straight back. Whoa. This was not supposed to happen. Rutherford himself had the perfect analogy for it. He said it was as unbelievable as firing a fast-moving bullet at a sheet of paper and having it bounce back. Can you imagine? It just made no sense. For something to bounce back like that, it must have hit something incredibly small, incredibly dense, and with a powerful positive charge, all packed into the middle of that otherwise empty atom. So, with this completely shocking piece of evidence, Rutherford had to scrap all the old theories. They just didn't work. He had to come up with a totally new picture of the atom, one that could explain all three of his observations, the ones that went through, the ones that bent, and the ones that bounced back. And his conclusions were just brilliant. Okay, so follow the logic. Most particles pass straight through? That means the atom must be mostly empty space. The few that get deflected? That means there's a small, positively charged thing in the middle. He called it the nucleus. And the ones that bounce straight back, That means the nucleus must be super tiny and super dense, packing almost all the atom's mass. And to make the whole atom neutral, the light, negative electrons must be orbiting that nucleus way out on the edges, kind of like planets orbiting the sun. This planetary model was a huge, huge step forward. I mean, it gave us the nucleus. We still use that basic picture today. It was an amazing piece of detective work. But, and this is a big but, there was a problem. A couple of really, really big, catastrophic problems, actually.
So here's the question that stumped everyone. If you have a negative electron orbiting a positive nucleus, why doesn't the atom just collapse? I mean, according to the physics everyone knew and trusted back then, Rutherford's model was completely impossible. It just shouldn't work.
And this leads us to two fatal flaws. The first one is called the death spiral, which sounds dramatic, and it is. See, the physics of the day said that any charged particle moving in a circle has to radiate energy. It has to. So that poor little electron should be losing energy constantly, spiraling closer and closer until, bam, it crashes into the nucleus. The whole atom would collapse in a split second. But they don't. Our world is stable. The second problem was about light. Rutherford's model predicted that atoms should give off a continuous rainbow of light. But when you actually look at them, they only emit very specific, sharp lines of color. It's more like a barcode than a rainbow. His model just couldn't explain this.
So our detective story has hit a wall. A major plot twist. Rutherford found the culprit, the nucleus, but his explanation of the crime scene didn't hold up. The model was unstable. And then another scientist enters the scene, a Danish physicist named Niels Bohr. And he comes along with an idea that was, well, it was so radical he basically had to say, what if the rules of physics are wrong?
Bohr's entire solution was built on this wild new idea called quantum theory. And the key word here is quantized. The best way to think about it is this. In our big, everyday world, things are continuous, like a ramp. You can stand anywhere on it. But at the tiny atomic level, Bohr said things are quantized, like stairs. You can be on step 1 or step 2, but you can't be in between. Energy for an electron comes in these fixed, specific pockets, or quanta. You can't have half a packet.
So Bohr took this crazy stairs idea and applied it to the atom. He said, look, electrons can't just orbit anywhere they want, like planets can. Nope, they're stuck on specific stairs, fixed energy levels, or shells. And here's the kicker. While an electron is on its designated stair, it just doesn't lose energy. It's a special quantum rule. Boom! Death spiral problem solved. And how do they move? They can jump from one stair to another. But to do that, they have to absorb or release one exact packet of energy. And that exact packet of energy corresponds to a specific color of light. Suddenly, the barcode spectrum made perfect sense. And when you put them side by side, you can really see the genius of it. Rutherford's model, using the old classical physics, gave us an unstable atom that should collapse. Bohr, by bravely introducing this new quantum rule, gave us a stable atom. Rutherford's atom should glow with a continuous rainbow. Bohr's atom emits a sharp barcode spectrum, which is exactly what we see in the real world. The theory finally matched reality. The case, it seemed, was closed. Now, Bohr's model was an absolute triumph. Don't get me wrong. It saved the day and gave us a working picture of the atom. But is the story really over? You know, in science, solving one mystery almost always opens a door to an even deeper one. Bohr's model worked beautifully, but it also raised some new, even weirder questions. Questions that would lead to the whole mind-bending world of quantum mechanics. So, it turns out, this detective story was far from over.